Hello and welcome. Heart disease is the leading cause of death with over 18.6 million lives taken globally in 2020, according to the data from the CDC. It is a complex and multifactorial condition that depends on various factors such as age, gender, ethnicity, genetics, medical history, and risky lifestyles such as tobacco use, unhealthy diet, alcohol use, and physical inactivity. However, many people are unaware or uncertain of the risk of developing heart disease. In this study, I aim to answer the question, can machine learning help people assess their personal risk of heart disease? Heart disease is a binary classification problem, meaning I have to predict whether a person has heart disease based on some input features. Heart disease risk factors are complex, interrelated, and vary from person to person. I plan to use population study statistics, focus on those factors that people can self-assess, and utilize machine learning to provide a personalized risk prediction prior to conducting a full checkup with a physician. The data is taken from the CDC's 2020 Behavioral Risk Factor Surveillance System Survey, which is conducted annually. It is a telephone survey about the United States residents' health status, containing over 400,000 rows and 279 unique columns regarding the health status and demographics of the individuals. The data is officially published in the XPT format, which has been transformed into a .hyper file for Tableau desktop. I use the application to first view the available features and extract the 33 most relevant features as a CSV file. The target data for the heart disease classification is labeled as MICHD in the original data dictionary and have two possible values, 1 meaning the person has heart disease and 2 meaning the person does not. The process begins with data loading, where the exported CSV file is loaded into the project. Then, the feature names were changed for better readability. Data exploration reviews 5 numerical features and the rest are categorical features. There are also 5 features that contain missing values. For the target variable, people who have heart disease make up 8.79% of all the data records. The survey contains people from ages 18 up to 80 or older, with the older generations making up the majority. There are demographic features, risk behavior-related features, health conditions features, difficulties in everyday life features, general health features, and finally, the numerical features such as BMI, height, weight, and sleep time. The next step is to pre-process and clean the data, starting with the missing values. Since there are only 5 columns with missing values, none over 1.5%, the rows containing missing data were dropped. Next, the categorical features were cleaned. In the survey, some were non-respond categories such as don't know, refuse, or missing. Since these only make up a very small amount of the data, these rows were also dropped. The yes and no answers were encoded as numbers 1 and 0, respectively. Then, all numerical features were checked for outliers and have them removed. After the data were dropped, the next step is to encode the data. Firstly, the categorical features such as BMI category, race, sex, and income level were hard-coded. Then, values with inherent order or hierarchy such as age and general health levels were ordinally encoded using maps as shown. Next, the numerical features were normalized using the min-max scalar into values between 0 and 1. This is possible because I have previously removed the outliers in the numerical data. Now, recall that there were significantly more people without heart disease than those that do. I decided to resample the data for people with heart disease. By resampling the minority class, I ensure that both classes have equal contribution to the model's training, and the model can learn to distinguish between them more accurately. Next, the correlation of the features were determined and ranked. The features with the high multicollinearity were removed, and only the columns with the highest correlations were selected. Note that has chronic conditions and has heart attack were 2 features dropped, and some of the features with slightly lower correlations were still kept. This is to generalize the model for a general person, as they may not be aware of such conditions, and the goal here is to base the model on general questions that can be answered by the person themselves. Finally, these 15 features were selected to fit the models. And this is the clean data. Now it's time for data modeling. The goal is to determine which classifier model has the best prediction in terms of the existence of heart disease based on the personal indicators information. There are a total of 7 classification models explored, each of which have been run through grid search CV to identify the best hyperparameters. And now, let's jump right to the first one. Logistic regression. It is a simple and efficient model, good for binary classification and doing categorical values. It is easy to interpret and can handle large datasets. Since the minority target data has been resampled, accuracy is a suitable metric of performance. The logistic regression model achieves 75.2% accuracy with very balanced precision and recall at similar level. Next, the rich classifier was used because it is good for binary classification, can handle high-dimensional datasets with many features, and it has threshold functions to assign the class label based on the size of the linear combination. The rich classifier performed nearly identically to the logistic regression, with ever so slightly lower accuracy. The next model is the naive-Bayes classifier, which is robust to outliers and are suitable for high-dimensional datasets with many features. However, it did much worse compared to the previous models at 70.4% accuracy. I believe it's because the naive Bayes assumes that the features are independent. Although, some risk factors for heart diseases such as age, blood pressure, cholesterol, and smoking might be correlated with one another, hence the poor accuracy and especially for heart disease recall. The k-nearest neighbors model assumes that all features are equally important and were good for small to medium-sized datasets. Despite that, the model performs as well as the first two with 76% accuracy. The decision tree is a good model for interpreting decision-making process and can handle categorical data and numerical features as well. With this model, an accuracy of 78.3% can be achieved, the highest one so far without overfitting as well. Up to this point, we have seen the classifier models with increasing accuracy. Each of them places emphasis on different features and have different degrees of errors and biases in different metrics. With the ensemble method, the previous models can be combined to produce a more accurate and reliable output. The voting classifier uses the logistic regression, rich classifier, decision tree, and KNN models independently and computes their individual output called vote. The class with maximum votes is then returned as the output. This achieves the accuracy of 77%. The stacking classifier combines the predictions from multiple well-performing machine learning models and make predictions that have better performance than any single model in the ensemble alone. At 80%, this is the highest accuracy so far. The last is a random forest classifier, which also uses the ensemble method. It is good for classification and can handle large datasets with high-dimensional features. At also 80%, making random forest classifier and the stacking classifier the two best performing models tested. And according to this model, the 3 most important features that determine the possibility of heart disease are age, general health conditions, and physical health conditions. Finally, to further improve the model, I propose using more and higher quality data by ensuring less missing data, collecting more balanced amount of responses from people with and without heart disease, so the data doesn't have to be resampled, and continue collecting up-to-date survey responses to update the model. This project is completely repeatable with new annual BRFSS survey dataset to be published by the CDC annually. The data can be transformed from an XPT file into a CSV file, and for future work, I propose developing a simple web page with forms for any people to fill in their health indicators, keep records of new data, and keep the data in the database up to date with more data without having to rely exclusively on the survey data alone. This concludes the presentation. Thank you and have a nice day.